For years, the world's most advanced microchips were protected by a technological wall that China was never supposed to climb. But in the high-security labs of Shenzhen, the impossible has just been built, and the global balance of power is shifting faster than anyone predicted.
All right, we're about to enter the high-NA lab.
Behind this highly secured door in an ASML clean room.
The impossible bottleneck. Imagine a race where every runner is trying to reach a finish line, but only one person in the entire world owns the shoes needed to get there. In the high-stakes, high-tech world of semiconductor manufacturing, those shoes are a machine called EUV lithography. For decades, the global semiconductor race hinged on one seemingly immovable assumption: China could never, under any circumstances, acquire this technology. Not because they lacked the talent or the ambition, but because the technology was locked inside a single Dutch company named ASML, protected by some of the strictest export controls in modern history. Without EUV machines, you simply cannot manufacture the most advanced semiconductor chips. And without those chips, you're effectively sidelined from the most competitive arenas of technology today: artificial intelligence, supercomputing, advanced mobile devices, and modern weapon systems. For years, Western governments and tech leaders alike believed this bottleneck was immovable. They assumed China was trapped at least a decade behind the cutting edge in chip manufacturing.
The development follows years of US restrictions aimed at limiting China's access to cutting-edge semiconductors.
But that long-held belief is crumbling. A groundbreaking, detailed investigation has unearthed something shocking. A secret laboratory in Shenzhen, China, has quietly built a working prototype EUV system. This machine exists, it's operational, and its emergence is forcing everyone from Silicon Valley boardrooms to the halls of Washington Power to discard their old timelines and rethink the future of technology dominance.
After years of Chinese government investments, the prototype can actually generate extreme ultraviolet light, but has not yet produced working chips.
The secret prototype in Shenzhen. This is not mere speculation or a rumor circulating on tech forums. This is a massive, tangible system reportedly occupying nearly an entire factory floor in Shenzhen, completed in early 2025 and currently undergoing rigorous testing. The machine has already demonstrated the ability to generate extreme ultraviolet light at the critical wavelength of 13.5 nanometers, the exact wavelength required for advanced chip lithography. While this prototype hasn't yet begun mass-producing millions of chips that power your smartphones or AI accelerators, the fact that it is generating the right kind of EUV light at all is a geopolitical earthquake. It's akin to discovering that while the rest of the world was dismissing a competitor as a long shot, that competitor quietly built a functional rocket engine that actually works. All along, people assumed China didn't even have the blueprints. Now, they have a working prototype. The level of secrecy surrounding this project is next-level cloak and dagger. Engineers working on the system reportedly received ID cards with fake names and were instructed to use aliases, even among their own teammates. The project is classified as an absolute matter of national security, with teams isolated from one another to prevent leaks. This is not a run-of-the-mill corporate initiative. This is a mission with strategic, national importance.
To etch microscopic circuit patterns onto silicon wafers, these machines are vital for producing the most advanced computer chips, powering everything from smartphones to artificial intelligence.
What is EUV lithography and why does it matter? To understand why this revelation is causing such a stir, you need to understand what EUV actually does. EUV stands for Extreme Ultraviolet Lithography, and it's the world's most precise kind of printer for semiconductors. Instead of ink, EUV machines use light to draw billions of tiny circuit patterns onto silicon wafers. These patterns are measured in nanometers, a scale thousands of times thinner than a human hair. The smaller and more precise these patterns are, the more transistors you can pack into a single chip. More transistors mean more powerful and energy-efficient processors.
While limited sales of NVIDIA's H200 chips have been approved, controls of the most advanced technologies remain tight.
This magic is what enables tech giants like NVIDIA, Apple, Qualcomm, and others to build chips that run everything from your smartphone and laptop to the AI servers powering the internet. Every modern AI system, every high-end smartphone, and every advanced military drone depends on chips produced using EUV lithography.
EUV lithography machines are the most expensive step in making every advanced microchip that powers the modern digital age: data centers, cars, and every single iPhone.
The ASML monopoly. For decades, the Dutch company ASML has held an effective monopoly on EUV machines. These machines are enormous. Each costs over $350 million, weighs about 180 tons, and contains hundreds of thousands of ultra-precise components sourced from global suppliers. ASML spent more than 20 years and billions of dollars to make this technology a reality. Because of export restrictions imposed mainly by Western governments, ASML has been forbidden from selling EUV machines to China. That means China's semiconductor industry has had to rely on older, less capable lithography technology, which is why many experts assume China would be stuck at least a decade behind in the race for cutting-edge chips. The Manhattan Project of chips. But China's approach isn't to accept defeat. Instead, it's been quietly building a Manhattan Project for chips. Why is this term being used? Because of the scale and intensity of the effort. Reports suggest the tech giant Huawei is at the heart of it, coordinating thousands of engineers across multiple labs and companies, all working in strict secrecy. This project didn't start from zero. China has spent years scouting talent, recruiting former engineers who once worked for ASML or related companies. These veterans bring the intimate, hard-to-learn, secret sauce, knowledge, the kind of insights that can't be found in manuals or patents. China's resourcefulness extends to hardware too. They've reportedly been acquiring older ASML lithography machines on the second-hand market and at auctions, carefully dismantling them to study each component. For parts they still cannot manufacture domestically, they've been sourcing restricted components from Japanese companies like Nikon and Canon, all while routing shipments through multiple countries to hide their ultimate destination. Brute force engineering. If you saw China's prototype next to an ASML machine, the difference would be striking. ASML's machines are sleek, highly refined, and about the size of a school bus. China's prototype, by contrast, is reportedly much larger and rougher around the edges. Unable to miniaturize certain components to the same precision, Chinese engineers have compensated by building them bigger and more powerfully to achieve the same effect. It's a brute force approach rather than a refined one. In terms of generating EUV light, ASML uses a technique where high-powered lasers hit tiny drops of tin 50,000 times per second to create the necessary photons. China, meanwhile, is experimenting with an alternative called laser-induced discharge plasma, LDP. It may not be as efficient or elegant, but it's a method they can develop independently and control without relying on foreign technology. The optics challenge, the final 20%. In any advanced engineering feat, there's a well-known rule of thumb. The first 80% of progress happens relatively quickly, but the last 20%, the final stretch, takes longer than everything else combined. This is precisely where China is currently stuck. The critical bottleneck now is the optics inside the EUV machines. These aren't just ordinary mirrors, they are the most precise objects ever made by humans. To put it in perspective, if one of these mirrors were enlarged to the size of a country, the tallest mountain on its surface would be less than 1 centimeter high. These mirrors must be polished to near perfection because even the tiniest speck of dust or the slightest vibration can ruin the chip-making process. To date, Western companies, particularly Carl Zeiss in Germany, maintain a significant technological lead in producing these optics. This integration phase, the stage where all components work together seamlessly, is where China faces its toughest challenge. They can generate EUV light, but can they reflect, focus, and control it perfectly enough to manufacture advanced chips reliably? This is the bottleneck that might hold them back or could become their breakthrough. The geopolitical earthquake of 2026. Why is this suddenly causing a panic in Silicon Valley and Washington? Because the timeline for Chinese chip independence has been dramatically accelerated. Before this revelation, analysts believed China would reach this stage no earlier than the mid-2030s. But the existence of a working prototype as early as 2025 means those timelines must be reconsidered. Internal Chinese targets reportedly aim to mass-produce EUV chips by 2028, while more cautious experts see 2030 as a realistic milestone for Chinese EUV chips hitting the market. If China pulls this off, the global semiconductor industry will split into two distinct spheres, a silicon curtain. On one side will be the Western-led ecosystem, spearheaded by the US, Europe, and Taiwan. On the other side will be a fully independent Chinese system, controlling everything from raw materials and machinery to final AI chip designs. This is not just about catching up, it's about potentially overtaking. China would no longer have to worry about sanctions, export restrictions, or supply chain choke points. They could control their own digital destiny. What happens next? The Shenzhen prototype is a clear signal that the West's strategy of freezing China's tech progress through export controls and sanctions hasn't worked as intended. Instead of slowing down, the pressure has seemingly forced China to build its own entire semiconductor ecosystem from the ground up. Will China master the final 20% of the optics challenge and scale production to mass levels by 2030? Or will the complexity of the physics involved prove too great a barrier even for their well-funded, highly motivated Manhattan project? One thing is certain, the race for technological supremacy is no longer a one-player game. The once unchallenged monopoly on EUV lithography is under threat, and the next few years will determine who truly controls the brainpower of the 21st century. So, what do you think? Can China pull off this extraordinary feat and close the gap, or even leap ahead in semiconductor technology? Or is the final 20% hurdle an insurmountable challenge that will keep them from mass production anytime soon? Drop your thoughts in the comments below. I read every single one of them. And if you want the real story behind the world's fastest-moving tech breakthroughs, make sure to like and subscribe to Charging Volt. We're covering the future, one chip at a time.